In previous lectures, I've not hesitated to say that this star is 100 light years away, or that galaxy is 3 billion light years away. But you may be wondering, how do you know the distances to such remote objects? I mean, it's one thing to watch your odometer click around as you drive across country, but imagine looking at the night sky. How do you figure out the distance to those tiny points of light? And yet knowing the distances is crucial to our cosmological story. If you think the stars lie at the same distance as the sun and the moon, as many pre-scientific cultures did, then the Earth becomes dominant, possibly primary cosmic player. But if instead stars are like the sun, but they're just faint because they're very far away, then we live in a radically different kind of universe, one in which the Earth shrinks into insignificance in the vastness of it all. So this is the topic for the lecture: how distances are measured. And as we'll learn, knowing distances doesn't just tell us the universe is really, really big. They do much more than that. They allow us to ascertain the intrinsic properties of objects, their true sizes and powers. They allow us to know how far back in time we're looking, which is extremely important in cosmology for constructing the history of the universe. And in the next lecture, we'll see that measuring accurate distances is essential in figuring out the properties of the universe as a whole, its expansion rate, its age, its geometry, and its composition. Now let me start with a very important point. There is no single method for measuring distances to astronomical objects. Some methods work for nearby objects, while other methods work only for more distant objects. The distances at which the various methods work overlap. So nearby methods are used to calibrate more distant methods, which in turn are used to calibrate yet more distant methods, and so on in what is called the distance ladder. Now, given our limited time, I'll talk about just 5 of the most important steps on this ladder, starting nearby and ending with the most distant galaxies. Now, the first 2 steps in the distance ladder make use of a standard surveying technique called triangulation, which astronomers often call parallax. So let's take a quick look at that now. Imagine a person looking at a foreground object against a more distant background. Actually, you could try doing this using your finger or a pencil as the object, looking alternately with your left eye and then your right eye. Your finger appears to jump across the background. Closer objects jump more, further objects jump less. Of course, our brains automatically use the difference between the images of the left and right eye to intuit the object's distance. But we want a more general method that works for any 2 viewpoints. Now, the amount of jump is given by this angle, which is, of course, the same as this apex angle. You can see that we have a long, skinny triangle with a base, a distance, and a little angle. And as you may recall from high school geometry, knowing any 2 of these gives you the third. So, for a skinny triangle, we have distance equals base length times 57.3 over the apex angle measured in degrees. Let's make a mental check. Smaller angles yield longer distances, which seems about right. And for a skinny triangle with 1 degree apex and a 1-inch base, the length is about 57.3 inches or 5 feet, which also seems about right. Now, for reasons that will become apparent shortly, astronomers often work with extremely tiny angles. So let's just look at those briefly now. We're all familiar with degrees, 90 degrees in a right angle, so 1 degree is already pretty small. Now, if you need much smaller angles, then an arc minute is a 60th of a degree, and an arc second is a 60th of an arc minute, which is a 3,600th of a degree. So back to our slim triangle with a 1-inch base. If we now make the apex angle 3,600 times smaller, so it's now just 1 arcsecond, then the length increases to 3,600 times 57.3, or about 206,000 inches, which is about 3¼ miles with a 1-inch base, so it's a really very skinny triangle. Okay, we're now ready for our first astronomical triangulation method. Now remember, the distance ladder starts close to home, and the first enormously important step on that ladder is to measure the size of the Earth's orbit around the Sun. Now the first attempt to do this using triangulation was in 1672, when the great Italian-French astronomer Giovanni Cassini observed the position of Mars from Paris, while his assistant, Jean Richet, observed the position of Mars at the same time from the coast of South America, 4,000 miles away. When they compared the two positions, they found a small shift of about 20 arcseconds, and from that, they could calculate a distance to Mars. And using that distance, they calculated the Earth-Sun distance that was actually only about 10% off the true value. Now, since then, there have been many attempts to use triangulation to measure the Earth-Sun distance. But now, they're really only of historical interest because modern measurements use huge radio telescopes to bounce radar pulses off Venus. Timing the reflected signal and knowing the relative distance to Venus and the Sun then gives an Earth-Sun distance to an accuracy of about 30 yards. Now, the true Earth-Sun distance, actually its average value, because the Earth's orbit is slightly elliptical, is called an astronomical unit, or AU, and it's very close to about 150 million kilometers, or 93 million miles. By human standards, it is, of course, a huge distance. If one step from here to here crosses the United States, New York to San Francisco, then the Sun is 20 miles away. So now that we have a securely measured orbit for the Earth, we're ready to move on to our next step in the distance ladder and reapply triangulation method to measure the distance to stars, using the Earth's orbit as the base for our skinny triangles. This is almost an identical illustration to our first one of human binocular vision, but it replaces the human head with the Earth's orbit. The position of a nearby star is observed twice, 6 months apart, from opposite sides of the orbit. Sure enough, as you can see from this little animation, nearby stars show a small jump against the backdrop of much more distant stars. Now, with a base of 2 astronomical units and a measured jump angle, the distance to these nearby stars can now be calculated using our handy triangle equation. Now, as usual, although this is simple in principle, in practice it is extremely difficult because the jump angles are extremely small. In fact, despite enormous efforts, it wasn't until 1838 that the great German mathematician and astronomer Friedrich Bessel finally measured these tiny parallax shifts, as they're called. For the nearest stars, the shift is about 1 arcsecond, with smaller shifts for more distant stars. Now, a 1 arcsecond shift is equivalent to trying to see the jump of an object 10 miles away by closing your right eye and then your left eye. Didn't quite do that right. It's no wonder it took great care and excellent instruments to see these tiny shifts. So what distances do we find for the nearby stars? Using our small angle equation, an apex angle of 1 arcsecond tells us that the distance is about 206,000 times the base. Now let's use light travel times to estimate this. Our orbit base is twice 8, that's 16 light minutes. So the distance is about 206,000 times that, or about 3 million light minutes, or 6 light years. So nearby stars are a few light years away. In human terms, this is an unimaginable distance. Returning to our one pace crosses the United States with the sun 20 miles away. To get to the nearest star, I would need to walk 30 times further than the moon. Now at this point I'd like to introduce and then immediately ignore a famous unit of distance that astronomers often use called the parsec. The word comes from a contraction of parallax and arcsecond, and it's simply the length of a slim triangle whose base is the radius of the Earth's orbit, 1 AU, and whose apex angle is 1 arcsecond. So from what we've just learned, you can see that a parsec is simply 206,000 astronomical units, or 3.26 light years, or a little more than 30 trillion kilometers. Now, although astronomers tend to use parsecs, actually, or kiloparsecs or even megaparsecs, in these lectures I'm going to continue to use light years instead, mainly because they give us the look-back time to objects in years, which is very convenient if your subject happens to be cosmology. But if you ever need to convert parsecs to light years, it's very easy. You just multiply by 3 and then add a bit. Now, despite the incredibly tiny parallax angles, modern technology has made huge advances. From the ground, atmospheric blurring limits the measurements to about 1/100th of an arcsecond. But above the atmosphere, you can achieve enormous improvements. So, since the 1990s, the European Hipparcos satellite measured parallax shifts for 120,000 stars with a precision of 1,000th of an arcsecond. And the satellite Gaia, which is Hipparcos' successor and due to be launched in 2011, will achieve 20 millionths of an arcsecond precision. That's the width of a human hair seen from 500 miles away. It'll give distances to millions of stars across the entire galaxy. If Gaia is successful, it'll be a truly wonderful project. Now, before moving on, I'd just like to make one historical point about the parallax shifts of stars. Because even the ancient Greeks knew that if the Earth went around the Sun, then there should be shifts in the star positions. And in the great debates over whether the Earth went round the Sun or the Sun went round the Earth, Aristotle argued that the Earth must be stationary. Otherwise, we would notice the stars shifting back and forth. See, for him, the alternative possibility, which was that the stars are so far away that their shifts were just too small to see the truth of the matter, was philosophically unacceptable, because it would imply an unreasonably big cosmos. And that wasn't the first time, nor was it the last time, that nature far outstrips our timid notions of what is or is not reasonable. Okay, now let's return to our distance ladder. You can see here the current limits of trigonometric parallax. It reaches only a small part of our galaxy. So we're going to need different methods to go further. Now, by far the most versatile method is to derive distances from objects with known luminosity. Now, this illustrates the method. In a row of similar candles, the further ones look fainter. Now, as long as we know the true power of the candle and we can measure how bright it appears to be, then we can figure out its distance. Of course, the key to this method is to find objects whose intrinsic brightness, what astronomers call luminosity, is already known. Basically, we need to know the intrinsic brightness of a candle. Now, this diagram spells out the method a bit more precisely. Imagine an object, a star or a galaxy, it really doesn't matter what, with a known luminosity, L. Now, the units of L are watts, just like the labels on light bulbs. As the light from that object moves out, it becomes spread over ever larger spheres. Now, at a distance d, the area of the sphere from high school geometry is A equals 4 pi d squared. Now, obviously, if we happen to be on that sphere, those L watts have been spread evenly over the A square meters, giving the famous inverse square law for apparent brightness. B equals L over A, which is L over 4 pi d squared, where the units of B are now in watts per square meter. Now, measuring B at the telescope is relatively easy. So as long as we know L, we can easily calculate the distance, d, using our simple equation. Now, the last 3 rungs of our distance ladder rely on this method, and they each use a type of object with known luminosity, certain kinds of stars, certain kinds of galaxies, and certain kinds of supernova explosions. So let's look at these in turn. To a casual observer, the stars in the sky seem not only fixed in position, but also in brightness. But this is not always the case. If you look carefully, night after night, a few stars change in brightness, becoming brighter, then dimmer, in a regular, periodic way. One of the most famous of these stars is called Delta Cepheus. Using normal binoculars, you can watch this star getting slowly brighter and dimmer relative to its neighbours, repeating its cycle about every 5.3 days, as it first swells and then shrinks, like this little animation shows. Now, in 1912, Henrietta Leavitt, who was working at the Harvard Observatory, noticed a very interesting property of this kind of Cepheid variable star, as we now call this class of star. Intrinsically luminous Cepheids pulsate slowly, while less luminous Cepheids pulsate quickly. This sort of makes sense, reasonable sense. Big stars breathe more slowly than small stars, a bit like elephants breathe more slowly than people, who breathe more slowly than mice. Anyway, it transpires that Cepheids define quite a tight period luminosity relation, like the one shown here. Of course, you still need to calibrate the relation by using parallax to measure the distances to a few Cepheids, but in fact that was one of the primary motivations for the Hipparcos satellite that I just mentioned a few minutes ago. Now, this kind of relation is extremely useful to astronomers because once you've measured the period of the star's variation, you can use the period luminosity relation to read off its true luminosity. And then using its apparent brightness in the sky, you can quickly find the distance using our simple inverse square law equation. So this is how Cepheids are used to find the distances to the nearest galaxies. You see, fortunately, Cepheids are really powerful stars, between 100 and 10,000 times more powerful than the Sun. So they can be seen quite far away as individual stars in nearby galaxies. This was, in fact, one of the primary tasks of the Hubble Space Telescope, to find Cepheids in other galaxies and measure their distances. This HST Key project, as it was called, was led by Wendy Friedman and was completed in 1999, giving distances to 800 Cepheids in 18 galaxies out as far away as 65 million light years. Now, with distances measured to these 18 galaxies, they can now be used to calibrate the next step in the distance ladder. Now, but before we look at that next step, I want to visit a wonderful piece of astronomical history in which Cepheids played a key role. See, prior to the 1920s, it wasn't known whether the spiral nebulae, which had been discovered in the mid-19th century, was simply single stars in formation within our own Milky Way system, or entire island universes, other galaxies, in their own right, external to the Milky Way. And the issue was so vexed that in 1920, Harlow Shapley and Herbert Curtis debated the question publicly in Washington, D.C., with in fact no firm conclusions. Well, then in 1923, Edwin Hubble used the then new 100-inch telescope on Mount Wilson to find and measure Cepheids in the Great Andromeda Spiral Nebula. And he found a distance of 1 million light years. Immediately, that placed it well outside the Milky Way. So that single observation confirmed nebulae were separate galaxies, and by implication, so were all the other spiral nebulae, and suddenly the universe was recognized to be an enormously bigger place than had been previously thought. Okay, let's now go to the fourth step on the distance ladder, which is going to get us out to about 500 million light years. The step uses a relation similar to the one we met for Cepheids, but this time it applies to entire spiral galaxies. The relationship was discovered in the 1970s by Brent Tully and Rick Fisher, and it takes the form of a tight correlation between the intrinsic luminosity of a spiral galaxy and its speed of rotation. Basically, big luminous spirals rotate fast, while small, low luminosity spirals rotate more slowly. You can probably guess how this is used to measure distances. Take a galaxy, measure its rotation speed, then use the Tully-Fisher relation to read off the galaxy's intrinsic luminosity, then compare that to the luminosity of the galaxy's apparent brightness, and then figure out the distance using our handy equation, B is L over 4 pi d squared. Now at this point you might be wondering, how could we measure the rotation speed of spiral galaxies? But I'd like to postpone that discussion to lecture 9. Briefly, astronomers can relatively easily measure the speeds of things using the Doppler effect. Again, something we'll meet in coming lectures. So using the Tully-Fisher method, fairly accurate distances have been measured to thousands of galaxies, but out as far as maybe a few 100 million light years, allowing many truly impressive studies of the structure and motion of the nearby universe, which is something we'll come back to in lecture 22. However, in the cosmic scheme of things, these galaxies are still relatively nearby, perhaps a few % of the way to our visible limit of 14 billion light years. If we're going to measure distances to really far away galaxies, let's say 10 billion light years, then we need to find something that is exceedingly luminous, but also with known luminosity. Well, in the last 10 years, a great deal of effort has finally yielded such a class of object. They're called white dwarf supernovae, or to use the astronomers' term, supernovae type 1a. And they provide the fifth and final rung on our distance ladder. There are two qualities that make these supernovae ideal for distance measurements. They have almost exactly the same luminosity when they explode, and they are extremely bright, so they can be seen very far away, out to 10 billion light years. Now, the reason the explosions are so uniform is that they all involve exactly the same type of thermonuclear bomb. As this artist's picture suggests, the supernova is thought to come from a rare kind of binary star in which the outer atmosphere of one normal star is pulled over onto its companion white dwarf star, which is just a dense, burned-out ball of carbon and oxygen, roughly the size of the Earth, but containing about as much mass as the Sun. As more mass piles on, the temperature in the interior of the white dwarf reaches a critical point at which thermonuclear fusion rips through the star, and in a few seconds the entire star explodes, creating an extremely bright fireball that can outshine an entire galaxy for several days. Here's a simple animation that illustrates a supernova event. A star rapidly appears and then slowly fades. More precisely, here's the so-called light curve, which shows the supernova's rapid appearance and then gradual fading over about 60 days. And here's a lovely example of a supernova in a nearby galaxy. Of course, these nearby supernovae in galaxies with known distances are very important because you can calculate their true luminosity and so calibrate the method. The most challenging task, but the most important one for cosmology, is to find extremely distant supernovae. For this, large telescopes are used on several consecutive nights to take deep images that contain thousands of faint galaxies. Each image is subtracted from the previous night's image so that any new object is immediately visible in the difference image. Often a spectrum is then taken to confirm the nature of the supernova, and its slow fading is followed over the next few weeks using the Hubble Space Telescope. Some of these supernovae are enormously distant, 5, 6, 7, 8 billion light years away, with look-back times half the age of the universe. As we'll see in Lecture 9, it's these extremely distant supernovae at the very end of the distance ladder that gave the first evidence for an accelerating expansion that then uncovered the existence of dark energy. Throughout this lecture, I've needed to simplify the story of how distances are measured. The true history is much more nuanced and troubled, and it's taken over 100 years to develop. In fact, until 15 years ago, the cumulative uncertainty was 50%, not very good. But in the last few years, it's seen enormous progress. The Hipparcos satellite measured parallaxes of nearby stars, including many Cepheids. The Hubble telescope has used Cepheids to measure distances to dozens of nearby galaxies. The Tully-Fisher and other methods have been greatly improved, and the intrinsic brightness of white dwarf supernovae have finally been calibrated. So that today, the combined uncertainty in the distance scale is more like 5 to 10%, a huge improvement. In future lectures, the importance of reliable distance estimates will return time and time again. And so although this lecture hasn't perhaps included much exotic material from the cosmological story itself, we've been gathering some hard but necessary material that needs to be in place before we can move forward with that story. Now, I want to end this lecture with a new method currently being explored, which promises to bypass the distance ladder completely and yield a simple trigonometric distance out to several billion light years. The method has been developed using this extremely interesting nearby galaxy. Right at the center is a small, 1 light-year-sized disk of gas that's orbiting around a massive black hole. The method works like this. Imagine we have a blobby ring of gas moving rapidly in a circular orbit. First, we measure the speed of a blob here and find it to be, let's say, 1,000 kilometers per second. Next, we follow the position of another blob in the ring here for a year and notice it moves by, say, 10 micro arc seconds across the sky, 10 millionths of an arc second. Since these two blobs have the same speed, then a year moving at 1,000 kilometers per second, which is about 30 billion kilometers, is the same as 10 micro arc seconds as seen from the Earth. So we have an exceedingly skinny triangle with a base of 30 billion kilometers and an angle of 10 micro arc seconds. Bingo! We have the distance to the galaxy. Now you may be wondering, how on earth can we measure those things? But it's possible using powerful radio telescopes. The method hasn't been fully developed yet, but in time it's hoped that it may ultimately yield distances out to 8 billion light-years with roughly 2% accuracy, which would be a great improvement and simplification over the conventional distance ladder. Now, measuring an accurate distance to a small number of rather unusual types of galaxies isn't itself particularly important. But what is important is that it allows you to measure the expansion of the universe with high precision. And that's our next topic for the next lecture.